Hello everybody, welcome into another lesson. So today we're going to continue on with similar triangles, and we have two new theorems for similar triangles. The first one here is the side angle side similarity theorem, otherwise known as the SAS Similarity Theorem. This theorem states that if two sides of one triangle are in proportion to two sides of another triangle, and the included angles of the two triangles are congruent, then the triangles are similar. So here to illustrate the point, I have triangle ABC and triangle DEF. If we look at triangle ABC, we have side AC with a length of 2, side DF with a length of 3. That would put it in the ratio of 2 to 3, so the scale factor would be 2 to 3. And then if we look at triangle ABC, we have side AB has a length of 4, side DF has a length of, side DE has a length of 6. If we take the ratio of AB to DE, 4 to 6 also turns into 2 to 3. So you have two sides of the triangle in proportion. And then in triangle ABC, angle A is congruent to angle D of triangle DEF. So therefore, by the side angle side similarity theorem, triangle ABC is similar to triangle DEF. So that one's not terribly hard to understand. There's one more theorem which actually is even easier than this. Which, let me write that out here real quick. Alright, and then the next theorem we have is the side-side-side similarity theorem. This theorem states that if the sides of one triangle are in proportion to the sides of another triangle, then the triangles are similar. Well, you really almost don't even need to call this a theorem, because based on the definition of similar polygons, and triangles are polygons, are they not? For polygons to be similar, all the sides are in proportion. So this is kind of a duh theorem. But anyway, to illustrate this theorem, again, we have triangles ABC and triangles DEF. I've kept the lengths the same. If we take AC to DF, we have the ratio 2 to 3, which would be our scale factor. If you take AB to DE, you have 4 to 6, which is also 2 to 3. Then if I take the corresponding side of ABC, which would be side BC, and compare it to the corresponding side of the other triangle, EF, I would have the ratio 6 to 9, which would also give me a ratio of 2 to 3. So therefore, triangle ABC is similar to triangle DEF. So those are pretty easy theorems to use. Those aren't bad at all. Now let's get into some exercises to put these into practice. Alright. So let's see here. Let me draw this bad boy. then let's see what we're given. Okay. So we're going to start out here with two triangles, and they are similar. It's already given to us that these are similar triangles. But for what reason are they similar? Well, I think one thing that's glaringly obvious is that angle BCA would be congruent to angle ECD by the fact that vertical angles are congruent. So we have congruent angles now in each of the triangles. Now, we want to see the scale factor. We need to see the scale factor. If you're looking at these, it's going to look like 6 would be in a scale factor. It'd be 6 would be in ratio to 15, and then 9 would be in ratio to 10. But here's the problem with that. That would definitely not give you the same scale factor, right? If you look at the corresponding parts of the triangles, they're kind of flipped. So in actuality, 6 would be in ratio to 10, which would give you a scale factor of 3 to 5. And then 9 would be in ratio with 15, since those are the corresponding parts of the triangles, which also would give you a scale factor of 3 to 5. So your scale factor is 3 to 5. So what you have here now, you do have the two similar triangles. You have two sets of sides that are in proportion to each other, and you have a congruent angle. You have the included angle that's congruent in each. So in this case, triangle ABC is similar to triangle, because we want to list it by the corresponding sides, triangle EDC by side angle side similarity. So by side angle side similarity theorem, triangle ABC is similar to triangle EDC. So you have to look at the diagram, see what you're given, and see which parts of the triangles are corresponding, because not everything is always as it first appears. All right, next. All right, so we have two triangles here. Angle A is 40. Angle B is 80. Now let's see here. Angle J in this triangle is 60. Angle H in this triangle is 80. Well, we don't know anything about the sides, but we know stuff about angles. If we could just find the missing angles, it would appear we could use the AA Similarity Postulate, the angle-angle similarity postulate. So we only so far have one congruent angle between each, which both are 80 degrees, but we don't know the other angles yet. Let's solve for angle C. We know the sum of the measures of the internal angles of a triangle is 180. So if you add 40 and 80, you get 120. Subtract that from 180, you get that the measure of angle C is 60. And what do you know? You now have two congruent angles between the triangles. So we can actually state that these two triangles are similar. So what triangles are similar? We can say triangle ABC. Triangle ABC is similar to what? We started with the 40-degree angle, then to 80, then to 60. So this would be similar to triangle THJ. You want to have the corresponding parts that are lined up when you name the two triangles. These are similar by the AA Similarity Postulate. So by the angle-angle similarity postulate, triangle ABC is similar to triangle THJ. Another good one. Let me see here. LKM. This is triangle LKM. OPN. All right, then what are we given about these triangles? This side has a length of 7.5. Angle K is 65 degrees. And then we have KM is 12. OP is 8. Angle P is 65 degrees. PN is going to be 5. Okay. Well, we definitely see we have two congruent angles in the triangles, right? So that's one thing working for us. We have, one congruent angle between each of them. One set of congruent angles, I should say. But then we're given two side lengths on each. So it's going to look like, if it's going to be similar, it's going to be by the side angle side similarity theorem. So let's see what we got here. Let's find the base of one to the other. So again, these two triangles are flipped. According to the corresponding sides of these, it looks like KM would correspond to OP. So in other words, 12 would correspond to 8, right? To get your ratio, to get your scale factor, the scale factor would be 3 to 2. So that could only mean then that 7.5 would correspond to 5. Which I think we want to get rid of the decimal in the numerator, so let's multiply the numerator and denominator both by 2. This would end up becoming 15 over 10, which would still turn into 3 to 2. So we have two pairs of opposite sides of the triangles that are in proportion, and then we have the included angle of each triangle that's congruent. So we can actually now determine that these two triangles are similar. That's going to be triangle LKM is going to be similar to triangle let's see, I want to word this right. Triangle NPO. When it's flipped, it's a little weird. So triangle LKM is similar to triangle MPO by the side-angle-side similarity theorem? That would be the answer. So LKM is similar to NPO by the side-angle-side similarity theorem. All right, this time they help us out and make this a little more obvious. For once, we have nothing flipped in these triangles, which is going to be very nice. Okay, let's see what they give us. So this side has a length of 9. This side has a length of 12. This side has a length of 10.5. How about the next triangle? 6, 8, and 7. All right. So we have two triangles. We are given information about the three sides. And it looks like none of them are flipped. They're all both standing in the same respective positions. So AC would be in proportion to XN. So that would be 9 to 6. 9 to 6 would give you a scale factor of 3 to 2. So then it also looks like AB would be in ratio to XR, which would give you 12 to 8, which would also give you a ratio of 3 to 2, your scale factor of 3 to 2. So that means CB has to be in proportion to NR, which would give you 10.5 to 7, which once again I'm going to suggest multiplying both numerator and denominator by 2 to get rid of your decimal. That would give you 21 to 14, which would coincidentally give you 3 to 2. So we're given that all three sides of the triangles are in proportion to each other. So we can now say that triangle ABC is similar to triangle XRN, this time by the side-side-side similarity theorem. So by the side-side-side similarity theorem, triangles ABC and XRN are similar to each other. Alright, so it looks like we have a smaller triangle inside of a bigger triangle. So we're going to be comparing similarity with one triangle inside of the other. All we have here is, see, 50 degrees for this. We have 130 degrees here. Okay. Well, let's start with something. We're only given angles, right? That's all they give us. Well, if we have two lines that are cut by a transversal and same side interior angles are supplementary, what does that mean? That means the two lines are parallel. So BC would run parallel to EF. We can now prove they're parallel since the same side interior angles are supplementary. Which means that angle AEF also has to be 50 degrees, does it not? So now between the smaller triangle and the big triangle, we have one congruent angle with them both being 50 degrees. Well, don't both the smaller triangle and the whole big triangle share angle A? So you're actually going to have two congruent angles in each triangle by default. So now we can actually conclude that triangle AEF is similar to triangle ABC by the angle-angle similarity postulate. So by the angle-angle similarity postulate, triangle AEF is similar to triangle ABC. So working with similar triangles in a way is nicer than working with congruent ones, because with similarity all you need are angles, where when it came to proving congruency that simply just wasn't enough. All right. So let's see, we're going to have two triangles here. Let's see what we're given now. This side is 20. This side is 31.5. This side is 21. This side is 30. Okay, so to start with, in each of the triangles we're given two sides. Well, a glaring thing that's obvious is that angle CAB is going to be congruent to angle SAR. Bivertical angles are congruent. So we now have two congruent angles here, one in each congruent to the other. So we do know something about at least one angle. Now what we need to determine are the corresponding parts of the triangles of these two sides of each. Are they in proportion to each other? In this case, it does go straight down that CA and SA correspond to each other. So of course you would take the ratio of them, 20 to 30. That would give you, of course, a scale factor of 2 to 3. Excuse me. And then BA and RA are also in proportion. So you'll take 21 to 31.5, which we should get rid of that decimal from the denominator. That would end up giving you 62. No, it wouldn't. We're only multiplying by 2. Excuse me. That would give me 42 over 63. Which would reduce to 2 to 3. So now we have two pairs of sides of these two triangles that are in proportion to each other, and the included angles that are in fact congruent. So these triangles are definitely similar. So this means triangle ABC is similar to triangle ARS by the side angle side similarity theorem. So by the side angle side similarity theorem, triangle ABC is similar to triangle ARS. Okay, I have some more exercises here, but we're going to determine if the triangles are even proportional. So we're going to be given some lengths. We're going to have a couple triangles here. We're going to be given some lengths. We're going to, and then we're going to see if they're similar, and then we're also going to find the scale factor. So, whoops, wrong one, wrong color. All right, here's A, B, C. Draw a bigger model here. This will be T, R, I. Let's see what we're given for lengths. Good news is for these exercises, we're only dealing with lengths. We're not dealing with any angles whatsoever in this one. Okay, so actually for the next 4 exercises, that's all we have left in this lesson. AB, let's see, BC is 8, then AC is 10. The lengths on triangle ABC are going to stay the same for the next 4 exercises, but the other ones will change. TR is 9. RI is 12. And then TI is 15. So if they're similar, it's definitely going to be by the side-side-side similarity theorem. That's the only theorem we're dealing with here. So we already would know the reason if they are similar, but we need to determine, are they similar? And then what's the scale factor? Actually, we're going to work on the scale factor first. I think that makes more sense. Looking at these 2 triangles, AB would be in ratio to TR. So you would take 6 to 9. Well, if you simplify that, you would get the ratio of 2 to 3. Then BC would correspond to RI, so you would take 8 to 12. Well, that would also turn into 2 to 3. And then AC would correspond to TI, so you would take 10 to 15, which would give you 2 to 3. So the scale factor in this case is going to be 2 to 3. And then we can say that triangle ABC is in fact similar to triangle TRI. So the scale factor ended up being 2 to 3. Triangle ABC is in fact similar to triangle TRI. Alright, 3 more exercises. Alright, ABC's lengths are staying the same, but TRI's are going to change throughout these. What are the next lengths we're given? 12, 22, and then 16. I get it, not everything is drawn to scale, but this is what I was given. Okay, so we need to determine, are these triangles similar? If so, what's the scale factor? So AB would correspond to TR. So you would take 6 to 12, which would obviously reduce to 1 to 2. Now then BC corresponds to RI. You would take 8 to 22, which is going to reduce to 4 to 11. Well, right away we can say these triangles are not similar because you have different ratios for the corresponding sides. They're not in proportion. So they are not similar in this case. As soon as you get a different ratio for different corresponding sides, they're not similar. They all have to have the same scale factor, the same ratio. So that one we can stop right there. All right, what's next? 2 more exercises. $20, $25, and then 15. Okay, so again, side AB would be in ratio to side TR. So take 6 to 20, which would reduce to 3 to 10. You have the ratio 3 to 10. So then how about BC to RI? That would be 8 to 25, which doesn't reduce any further. So right away we have 2 different ratios for the different sides, so these triangles are not similar. So there, they are not similar. And that leaves one more exercise. All right, what's side TR this time? 10. Side RI has length of 7.5. This is going to be interesting. And then side TI has length of 12.5. So let's go with the corresponding sides here. Let's start out. AB would correspond to TR, so start with 6 to 10. What does 6 to 10 reduce to? 3 to 5. All right, then BC corresponds to RI, which would be 8 to 7.5. You multiply both by 2 to get rid of the decimal, you get 16 to 15, which doesn't reduce any further. So right away, we can determine these triangles are not similar. So these 2 triangles are not similar whatsoever. So that's it. That's really it for the lesson. There were 2 easy theorems today that you could put in your toolbox in addition to what we learned yesterday. So tomorrow's lesson, or I hope it's tomorrow. God forbid something come up, but it should be tomorrow. It'll be about proportional lengths of triangles. We're going to get into that for similar triangles. So I hope everyone has a great day. Take care.